Hello and welcome back. In this video, we'll move on to chapter 25, continuing to talk about simulation. There's no mini exercise associated with this video, but in this one, we'll start to build a model that will be a good sort of simplified base case that you can build off of as you work on the fifth assignment. So the fifth assignment will be a much more involved version of the model we'll start to build here. So let's get started. We talked about simulation a little bit already, and some of its benefits, right? A range of possible outcomes. It can be path dependent in that, for example, we'll build a retirement savings model and we'll see the path dependence in that, well, what if I lose a lot of money with highly negative returns early in my retirement savings? How does the rest of the path look after that, right? Versus, oh, what if I have really high returns early on in my savings? So we'll take a closer look at the benefits of simulation. If we were meeting in person, we would work on simulating pi. And if you're interested in it, feel free to take a look at it. In the interest of time, we won't work on this exercise here. But if you want to see how it works, or if you want to take a crack at simulating pi, feel free to let me know. But let's look at a retirement savings simulation. Right? Here's a basic retirement savings problem. And if we ignore the variation in returns, right, if we assume a return of 8% per year no matter what, this is a basic time value of money problem, right? You could solve for how much this client would have saved after 20 years, a 20-year annuity of $15,000 savings per year, right? See if you can find the future value on your own. Let's do it together as well. So let's see, if we've got a discount rate of 8%, as we said, we save for 20 years, say the payment is negative 15,000, and there's no present value, so we could just leave that out. The future value of a 20-year annuity of $15,000 savings with a discount rate of 8% per year, you'd end up with $686,000, right? So that's ignoring variability in returns, assuming that return is 8% per year every single year. But what if we incorporate uncertainty? What if returns follow a normal distribution and some years they're above 8%, some years they're way below 8%, and so on? That's the model we're going to build now. I've got a spreadsheet to get us started under in-class exercises. April 21st, Monte Carlo and portfolio simulation. Let's open it up. And so what the spreadsheet shows us is some architecture to track how the portfolio's value will grow over time. And I made some references to some of the parameters of the simulation so that if you change some of these, for example, it's possible to change the whole simulation without too much trouble. But let's do a brief review of how to simulate normally distributed returns, remember? So the kernel that kind of feeds that is the rand function, right? Some random number between 0 and 1. If we take this to be a percentile, right, then the norm.in function would tell us, okay, what's the 75th percentile of a normal distribution with a mean of 8% per year and a standard deviation of 14% per year, right? So norm.inv, first argument is rand, and then the second argument is the mean, and the third argument is the standard deviation. As I hit enter, the random number is going to update. But let's see, the 29th percentile of this distribution is a return of about 0.26%, pretty low. The 77th percentile, 78th percentile, right? Well above mean return, 19% in a given year. So we're going to simulate returns each year. And then we're also going to simulate how the account value changes as we add $15,000 per year, right? So let's see. Let me start the first. If we were to start this model, right? Why don't I hide some of these rows? Just want to try to make it so that you can see, okay? So suppose we make the deposits, and then that grows at some simulated return with a mean of 8% and standard deviation of 14%, right? So in year one, how much would we have after year one? It would be the yearly deposit times 1 plus some simulated normally distributed return, 1 plus norm.inv, right? So 1 plus a return that we earn, which comes from a normal distribution. So 15,000 times 1 plus norm.inv, where the first argument is the RAND function. Second argument is the standard deviation. There we go. So this is how much our account would grow in the first year, given some normally distributed random return, which we'll generate. So it looks like it grew a little bit here, given the formula that we put in. And why don't I make the cell reference to the payment, the annual deposit absolute. Let's also lock the mean and standard deviation, because we're going to copy and paste this down and do 1,000 simulations in this case. So in year 2, the formula will look similar, but with a little twist, right? After 2 years, what will the balance look like? Well, it'll be this previous year's balance times 1 plus a simulated return again. Norm.in, 1 plus the normally distributed simulated return. Hopefully we're getting comfortable with simulating normally distributed data. So here's how the previous balance would grow based on the simulated return. And then let's assume we add, going forward, we assume we add the payment at the end of the period. Does that make sense, right? So we'll assume that, okay, the previous year's account balance grows at a rate of 8% per year on average, with the standard deviation of 14%. And then at the end of the year, right, at the end of the year, we add $15,000. It's just an assumption of the model. We could say that, adjust it to see how it looks if we add the payment at the beginning of the period. But let's set it up like that. So each year we add $15,000, and then we also, before that, we simulate how the beginning account balance will grow or decline depending on a positive or negative return. So what I'll do is we want to keep this cell reference to B2, right? The previous balance, we want to keep that relative, not locked, not absolute. But let's lock the mean, the standard deviation, and the annual deposits. All right. So in the next video, we'll build out this model and talk about, see what we'll do with it, and then also talk about how it can form the basis for the 5th assignment. All right. Thanks for tuning in as always.